In this video, we're going to talk about what actually happens when we form a solution. So again, we want to think about the particulate level. So what's happening with our molecules, ions, and atoms inside our component or our solute whenever it dissolves. So we want to think about ionic solutes and covalent solutes separately. They do two different things. Ionic is going to break into ions. So for example, if I have something like sodium chloride, which is table salt, and I have that as my solute, it is a solid. If I put it into water and it dissolves, it breaks apart into sodium ions and chloride ions. So I know the charge. We did this back with ionic chapter based on group number. Sodium is in group 1, chloride is in group 7, so +1 and -1. State of matter here, these are both going to be aqueous. So aqueous is represented with AQ, and this is what tells me that salt is dissolved in water. So this reaction here is showing that the solid sodium chloride is being dissolved in water. So that one molecule of sodium chloride breaks into one molecule of sodium and one ion of sodium and one ion of chloride. So one particle is breaking up into two particles. And we're going to talk more about that later in this chapter. Sugar is a covalent molecule. It has the formula C12H22O11. When you put a covalent molecule into water or any other solvent, if it dissolves, it will not break apart. So one particle of sugar will remain one particle of sugar once dissolved. So if I take that solid sugar, so here's my solid sugar molecule, I'm going to put it in water and it stays the same, C12H22O11. Now instead of a solid, it is aqueous, which tells me that it has been dissolved into water. So dissolved ions when you have a ionic compound, dissolved molecules when you have a covalent compound. When ionic compounds dissolve and break apart into ions, what happens is we get what we call hydration of those ions. So your ions are going to have either a negative charge or a positive charge, and you'll have both when you have an ionic compound. Your water molecule, if we think back to geometries and polarity, water is a polar molecule. Oxygen is more electronegative, so we've got that negative partial charge at the top of the molecule, which leaves the hydrogens as partially positive. So when you get these charged ions floating around inside of this water that is polar, the negative ions are going to interact with the hydrogen atoms, and the positive ions are going to interact with the oxygen atoms. So that's what we're showing in this image. Here's your chloride ion, which is negative, and notice how it's interacting with the hydrogen atoms on the water molecule. Here's your potassium ion, which is positive, and it's interacting with the negative half of the water molecule, or the oxygen. So this is your hydration of ions, and this is what causes some ionic compounds to dissolve. Doing this stabilizes the system. It prefers to be broken apart and having the water molecules surrounding the ions. There are some ionic compounds that are not soluble. They would prefer to stay in the solid state, linked up to each other, and not have water be involved. And we'll talk about which ones prefer ions versus solid state in a little bit with solubility rules. So there's a couple of factors that can affect how fast something will dissolve, or the rate of solution formation. So one would be the state of subdivision of the solute. And what that really comes down to is particle size. So for example, if you take a whole aspirin tablet, put it in water, it's not really going to dissolve very much, if at all. If you crush it up, some of it will dissolve. So it's really about surface area. How much of that solid is actually being able to interact with the water. The more that can interact, the faster it will dissolve. For the next one, it says degree of agitation during solution preparation. So this is stirring. if you stir something, your solid is going to dissolve much more quickly than if you just dump it in and let it set. So this again is giving more interaction between the solvent and the solute, which is going to increase the rate of solution formation. Third one, temperature of the solution components. This is kind of like stirring. So remember, temperature is increasing the kinetic energy of your molecules, making them move around faster. So they're moving around more on their own, interacting more, and therefore dissolving more quickly and more quickly forming a solution. So here we're going to decide whether the following actions will increase or decrease the rate of dissolving. First one says we're going to heat the saltwater mixture. And we just said whenever we heat the mixture, it will increase the rate of forming the solution. The salt will dissolve more quickly. Second says we're going to shake the saltwater mixture, which, much like stirring, is going to increase the rate of solution formation. The third one says we're going to heat the table salt prior to adding it to the water. Heating the salt, unless you heat it to a crazy high temperature, is not going to melt. It's going to stay a solid, and the increase in temperature is not going to stick around. So really it's not going to change much at all. If instead I heated the water before adding in the salt, that water will hold the heat for a while, then the system is still warm and you will again increase the rate of solution formation.